Welcome to Claxton's first ever knowledge sharing webinar entitled A Supplier View of Structural Integrity. I'm Andy Norman and I am the Brand and Marketing Manager for Claxton Engineering, your webinar organiser today. Claxton are very excited to launch our new webinar channel today, and we have a programme of online knowledge sharing events planned over the coming months. We hope to cover a broad range of subjects, but if you have a specific theme or idea that you'd like us to cover, please let us know. Before we start, I just wanted to make a moment to ensure that everyone is ready and familiar with the webinar control panel. Firstly, you show a control panel on the right hand side of your screen. You may minimize this panel by clicking on the double arrow button in the upper left hand corner. You may expand the panel by clicking the same button. Lastly, unfortunately, the submit questions using the chat pane located near the bottom of the control panel is not available today. However, there will be an opportunity after the session to submit any questions to info@claxtonengineering.com. Okay, if I can start by introducing you to today's presenter, Anne Vicens. Anne is the product lead for our structures portfolio of products here at Claxton and has been with the company for 8 years. With a bachelor's degree in industrial engineering, Anne has worked for a number of oil companies, including Supplier and UWG. Over the years, Anne has worked together with a number of clients across the world to project manage conductor guide centralizer installations. She has also been involved with significant major pre-drill developments, which have benefited from Claxton's designed and installed drilling templates. Anne's innate understanding and knowledge of the well conductor environment enables her to add significant value at all stages of the project process, as this presentation will demonstrate today. I'm therefore delighted to introduce you to Anne Vicens.
Thank you, Andy. Well, let me just start by saying good morning or afternoon, depending on where you are. I would like also start by thanking you all for attending this presentation. It's our intention with this webinar to give you an idea of the type of asset integrity issues that we see in our specific line of work, and some ways in which these problems can and have been addressed in the past as well. On the agenda, I will start by letting you know a little bit about Claxton and what we do, and they go through the main scope of the presentation. The idea will be to highlight first good practices that we have found have helped us when running with a project, but also cover some of the problems encountered and examples of how we have solved those or how we fixed them. As per Andy's instructions before, if you have any comments as well that you might think could help improve the quality of the webinars, please let us know. Also, and quite importantly, if you have any specific issues around the subject of asset integrity, please let us know also through your feedback. This will be invaluable feedback for us and will help us develop not only these sessions, but also our services to make sure that we are really addressing all the industry actually needs from us as well. Right, who we are at Claxton. We were formed in 1985, quite small. Bob Claxton founded it, a man with a forklift basically. But now we have been growing, and we've been in the business for now 30 years. As I said, we started quite small, but even with the current industry pressures, we have been growing, and it's the plan to continue doing so. Our main base is in Great Yarmouth in the UK, but we also have offices in Aberdeen, in Norway, the Middle East and the Far East. As I said before, although we're growing, we're still a relatively small company, which allows us to be responsive and flexible to the industry ongoing demands and achieve deliveries that perhaps some of the bigger players will not be able to accommodate in some cases. So that's one of the reasons why clients do come to us. In terms of our main areas of expertise, you'll see there's some examples of our areas of expertise, but our main areas of expertise are on drilling riser systems, decommissioning, and structures. With the riser systems, we are very experienced, as well as supplying new systems for some of our clients. We also come with a big inventory of risers as part of our rental fleet. These, together with running tools, adapters, and some of our tensioning equipment as well, which is another one of our product lines, means that we can cover this whole scope of work for our clients. We have had quite an important growth as well on the decommissioning side. We have Claxton's own abrasive coating system, it's called Sabre, as well as our own abandonment tool called SWAT. And as well as having these tools, we also have all the necessary auxiliary equipment for cutting and recovering the wells, which includes drilling and pinning machines, bandsaws, etc. Under our structures offering, we supply for new developments, so scopes of supplies such as pre-drilling templates, centralizers, leg hatches, drill bushings. But we also have the other side of the spectrum, which is to do with asset life extension, which is the area that we're covering in this presentation. And under this banner, we provide replacement guides, centralizers, structural guides, clamps, casing repairs, and slot recoveries as well. We also have other products that are shown in the slide that are on occasions auxiliary to the main three areas, but that can run as an independent scope of work as well. From this short summary, you might have noticed that we're quite well positioned to offer our products and services from the early stages of the new development through to the maintenance and life extension, if applicable, all the way through to the commissioning or the final abandonment. Right. Before getting into the details of best practices and common problems, it's probably a good idea to start to define how we determine or how we evaluate the structural integrity of an asset. Suppose an obvious answer will be that the details of what a particular structural component should be like can be extracted from the original drawings or its functional design specification. During that initial phase, the interfaces, what they require design life, as well as the environmental loads or challenges or interfaces would have been analyzed to come to a final sort of practical and working solution. However, the point is that we shouldn't really forget that the moment the equipment starts its service, it also starts degrading. Certain assumptions that we use in the original design phase might not be applicable anymore. Minimum requirements and codes could have changed. Changes made to the surrounding area that could have affected the performance of the asset. Or the environmental conditions and its effect on the equipment could have been underestimated, because those also were based on assumptions. Something else to consider is the reason for reviewing the integrity of the assets. So you could be reviewing it as part of a systematic maintenance plan to make sure no issues are encountered during its design life. Or is it that you're looking to extend the life of the asset, which will be a different set of considerations. Having in mind that final goal, when carrying out the assessment, will be key to help making the right decision and allocating the resources in the most efficient way possible. It is because of these reasons that we think that asset life integrity should evaluate the initial design considerations, which is what we have there on the screen. What was the original design life? What loadings was expected to take? Which interfaces were considered key? Evaluating these against the current conditions might bring light to the root cause of issues with the equipment. So it's important to make that comparison. When we mention here on the slide caring for the assets, this includes inspections and maintenance to keep them in working order. Managing structural integrity requires a well-developed maintenance program that considers active components that are typically easily detectable, as any issue would mean they stop working. However, you'll also have passive components that appear to be functioning normally until the moment of failure, like appearance of a leakage, for example, from a corroded pipe. So it's not until actual failure has happened that you realize there's a problem. So another thing will be understanding the risk. This risk can be minor and affecting perhaps only the component, or could have potential implications for the whole asset. So when these risks are understood, is when the appropriate mitigating measures can be put in place to mitigate that risk. Record keeping is something that we'll be repeating a little bit through the presentation, but it's quite an important aspect and quite often an area of problem for this type of project. But it's a particular important aspect that, as I say, is overlooked at the different stages of an asset, the asset life. This means keeping not only the original drawings, but adequately noting any changes, modifications, refurbishments, and changes in its working parameters or the interfaces as well. If all this is up to date, then any additional work that is carried out is also updated, then the process to design, supply, or adapt this change will be greatly simplified. Understanding what the criterion signs are that we should be using to determine the type of measure or action is also important, because it will basically help us determine what type of solution or what steps do we really want to take, put in place. If we're talking about an isolated event, for example, then the actions will be different than if the problem has widespread to different equipment and areas. Also, if there is of difficult access that prevents correct inspection, we might need to be more conservative on our approach, and it's likely it will not get the same level of attention as other components. And that's another area that is quite important in terms of asset life extension. The access to some of these locations can be tricky in itself, on operation on itself. As the subject of discussion is quite broad, we will concentrate on good practices, common problems, and ways to solve them. This, of course, based on our specific experience on the subject. The design life of equipment, typically for the offshore industry, is set to about 20 to 25 years for structural elements on offshore platforms, should be, in theory, the minimum time the equipment should be able to reach in working conditions. But as we discussed before, the conditions under which the equipment was originally designed might have changed, so part of that initial stage should consider likely changes, modifications if possible as well. A big part of carrying a good design is making sure its function is not considered in isolation, but on how it will interface with other components and processes throughout its life. This will help to determine how these interfaces could potentially affect its performance, or if the component function could have an effect on other items, for example. It's easy to overlook potential interface issues when evaluating one component, so the best way to carry out the task is by methodically going through the different stages of the component's life. Then, after doing that, if you map the components in its surroundings as part of the system, then you'll have a better idea of what all the interfaces are. The design will then need to consider these aspects, but make sure not to neglect the inspection phase or phases of the equipment as well, because that's another area of potential problems. It's not uncommon for structural elements to be fitted in a way that makes access for inspections unnecessarily impractical. So something might be fitted in a position that you cannot get access unless you have to actually get rid of another structural element before you can actually reach the equipment. So, and this type of, if this is complicated in this manner, that perhaps might mean that you'll need a bigger team to carry out the work and more preparation. So the idea is to perhaps try to design options that require smaller and less specialized teams to carry out the maintenance as opposed to a specialized team. In terms of asset integrity, our main expertise lies with conductor integrity. It's because of this that we want to highlight best practices during the planning stages for centralization, and that's for both during the drilling phase as well as when running the conductors and casings, cementing the conductor, in this case, VIV, vortex into vibration. And we also include a little word of caution, if anything, on the commissioning, just because we have involvement in that aspect in our company, and there's potential things that can be problems that can be avoided if proper care is taken during the asset life extension or the maintenance stage of the project. As I mentioned before, centralization is a key issue for the structural integrity of conductors. So what you have is you have a big clearance between the conductor guides and the drill string once you first drill the wells, which would mean potential issues with the centralization during spudding. And that could end up translating into considerable misalignment between your drilling hole, or your drilled hole, and the conductor guides. This misalignment by itself represents already a problem to the conductor in terms of stress to the material in its particular. However, another problem as well could be when you actually start carrying out the cementing work for the conductor. If the conductor is lined to one side of the hole, then you potentially have the problem of the cement not actually going even around all the conductor. So you'll have a poor cement job on the conductor section, which can bring problems not only during its design life, but also later on when it comes to the commissioning. It is for these reasons that we think it is of great importance to control this initial offset. And a way to do so is waiting for slack tide, and just making sure that your drill string is central within the lower guide before you actually start spotting. But another way of doing this as well is by making use of centralizer or drill bushing. The purpose of this item is to centralize your string within the lower guide of your offshore platform or drilling template, if there's one. The alternative to this would be, as I said, to wait for slack tide, and then you'll have to lower quite carefully to the seabed, and ROV should monitor the operation as well, just to make sure that the relative position of the drill string within the lowest guide before spotting is central. Once you've taken care of the centralization of your drill string, then we also have to look at centralization of the conductors. So significant damage can occur if centralization is not considered, and this damage can be not only on the conductor but also on the jacket guides and on the flow lines as well. So lateral support for work conductors is required just to withstand the loads, and in the little diagram on the screen you'll notice that there's some loads shown in the sketch. You have wave and current loads identified there. There's a typical profile of wave and current loads that's typical for the North Sea, the profile. These are shown in the sketch as well, but as I said, for some other locations, not in the North Sea, those environmental loads might be a little bit more benign, but these values should be considerably reduced in some other locations, as I just said. But the important thing is the RISE analysis should confirm the project-specific load profile, and that can be checked. Just make sure that your design accounts for those lateral loads. Wave and slam impact as well. If the clearance between your conductors and your guide is not reduced, there is a risk of the conductor slamming against the guides. There's also wave action that can have an orbital movement. So it's not just a lateral load, but orbital movement of the conductor that has to be considered, especially for the wearing effect they could have. And that's one of the reasons why some of the applications using alternative materials to fabricate the steel do not work because of the wearing effect. This movement is, of course, worsened if the clearances are bigger. There's also offset between the well and the jacket. And what we covered in the previous slide, if you control that centralization during spotting, that should be minimized. But that's something else that needs to be considered. There's also the compression from surface loads, and that is going to be of particular importance on the lower section of the conductor requiring support to prevent the collapsing, but should still be flexible enough to allow the tieback, if necessary, tieback from seabed to surface. There's also right rotation, as shown there as well. And that needs to be controlled for the effect it could have with controlling the flow line movement, and should be addressed typically as a minimum. You address this by centralizing or addressing the splash zone and the cellar deck levels. The RISE analysis should also provide guidance regarding the maximum allowable clearance at each level. It is important that these assumptions on the analysis consider the minimum required clearance just for running the conductor. So there's a minimum clearance that we need just to be able to run the conductor through the guides, and that RISE analysis should consider that and should make assumptions that are achievable in the real life. The space out and its tolerance has also to be considered. If there is considerable uncertainty about the tally or the space out, then the length of the centralizers should be perhaps adjusted to reflect this uncertainty. So if you know that you're going to be accurate to 0.5 meters, then you might want to increase the length of your centralizer. So you can cover your whole length of your can plus the additional 0.5 meters of potential error. Or another alternative, obviously, is to review your process of preparing the tally space and see if you can reduce that error. Another key piece of information to know is if the conductor will be run after drilling or if it will be driven. If the conductor is going to be driven, then the centralizers cannot be pre-installed, but will instead be retrofitted. Our typical sort of pre-installed centralizers are designed for high lateral loads, but not actual loads. And besides that, is the uncertainty of where the centralizer will land. Even if the centralizers could take the actual loads, you wouldn't know exactly where the centralizer section, the conductor where the centralizer was installed, will end up relevant to the guide. So that's the reason why they're retrofitted. The primary cementing job of the conductor is of great importance for the integrity of the whole well completion. We already covered centralization during drilling to avoid potential issues during the cementing of the conductor. But apart from these, there are other checks and measures that can be put in place to make sure the quality of the cement job ends up being what was considered during the analysis and design phase. So cementers will typically pump a considerable percentage of excess of slurry as a standard practice. But this percentage will also depend perhaps on several factors to do with the formation characteristics, if it's an area that loses a lot of fluid. Prior experience in the area as well is important. If it's not a new well, then there will be records of how the previous primary jobs went. As an additional contingency, a secondary system to deliver the cement to the top section of the hole might also be considered. Operationally, things will be greatly simplified if these considerations were also discussed during the design stage, of course, because then you can fit something in advance. Ultimately, the design of the completion relies on the riser analysis and its results. And among other parameters, the analysis will rely on a specific point of fixity of the conductor. So it is key to be able to achieve, at the very least, a quality cement to this level. If this is not achieved, then you don't know all the assumptions that were made during the design phase might be wrong. So reaching this point of fixity is a way of making sure that the design choices for all different components of the completion are valid and hence optimize the fatigue life of your conductor. Vortex-induced vibration, or VIV, is an important source of fatigue or damage in the offshore oil exploration and production risers, basically. It can cause serious stress to the riser conductor systems, and this will be either by reducing the fatigue characteristics of the system, or in some extreme cases, that can cause physical damage to the riser and their components as well. The vibration induced in elastic structures by vortex shedding is of practical importance because of its potentially quite destructive to pipelines and marine risers. When the vortex shedding frequency approaches the natural frequency of a marine riser, the cylinder takes control of the shedding process, causing the vortices to be shed at a frequency close to its natural frequency. It's all a little bit sort of complicated, but this phenomenon, this is what they call vortex shedding lock-ins or synchronization. And under these lock-in conditions, large resonant oscillations occur, and what they call lift forces are amplified due to increase in vortex strength. So what this means is you'll have large responses in both directions give rise to these oscillatory stresses. And if these stresses persist, then significant fatigue damage may occur. So there's things that you can do for this. There's these VIV suppression devices that are used to negate the impact of this. The pictures that you see on your slides show, the one in yellow shows some strakes They are designed to disrupt the formation of these vertices around the riser. The fairings in the picture on to the right in black, in the other hand, are designed to smooth the flow and prevent some turbulence. And just in summary, when you have this, when the VIV presents as cross flow, that's when it's the worst potential problems, because you have potential structural damage as well as fatigue. As I say, it's the worst case scenario. As the vortices, what happens is they break one wave first and then the other, and that makes the oscillations to increase. When it's in line, there's potential fatigue issues, but in some cases you can sort of live with it. Well, that's why the analysis will let you know, there's a calculation, and then they will let you know if you actually have the possibility of VIV presenting itself, in which case you might consider some of these devices to avoid getting potential issues with your equipment. Now, I said before as well that I was going to include a sort of a word of caution in terms of the commissioning. The main reason for mentioning the commissioning is just as some advice or a suggestion. The care we take on the assets during their life and how good we are at keeping the records will be invaluable when the time comes to the commissioning. Knowing which structural components are sound and can be relied upon will save a considerable amount of time and money, as well as making the overall operation safer. If you see the pictures there on your slide, there's a couple of examples where the decommissioning phase was quite a complicated one, and that, as you can see, was because of the condition of the platform. The number of cuts and leaves greatly increases when there's uncertainty of the condition of structure of the different structural elements. And as you can imagine, in a case like shown in the picture, then something that could have perhaps been done a lot easier and safer basically required an incredible amount of work and planning. Now, as I said, we were going to cover some of the common problems that we see sort of in our day-to-day here at Claxton. Centralization is one of them. Guides or conductors that have been damaged, corrosion issues, as well as with formations that have been depleted and perhaps are no longer economically viable. For all the above problems, being able to access detailed records will really simplify the process of designing, sourcing, and carrying out any of the remedial work. If these records are not available, which happens in a lot of occasions, there is the potential for extensive surveys that will be required, and the problem with that obviously is that they add cost and time as well. An important aspect of the projects we see to do with asset life extension is that they require a considerable amount of engineering. So the problems might be similar, but the applications always have very specific interfaces or additional access challenges or specific project parameters as well. So there's a fair amount of engineering involved in this type of project. Right, when it comes to the centralization, a common problem that we've seen, in particular in some of the older platforms, is that perhaps centralization was not considered at all at the beginning, so there's no centralizers installed. It could also be that the previously installed centralizers have fallen down or slipped, so anyhow, there's no centralization within the guide and the conductors anymore. And those conductors actually do need the lateral support to be able to minimize the fatigue. It's also possible that there were errors in the tally when the original conductors were run, which means that the principal centralizers are not located within the guide, which could be one of the reasons why they're no longer within the guide. Another problem is also failure of the original centralizers, as I mentioned before. The failure could be for a number of reasons. It could be obviously a mistake on the original design, but it also could be that equipment was damaged perhaps during installation or during its life, or it basically just has exceeded its design life. It's not uncommon for some of our older platforms. Equipment was designed originally for 15 years and they have far exceeded their expected life. So they just need some attention basically. For all these cases, again, reviewing the records will be a key thing to do. Information recorded during the installation or during the inspections could really help make sure that if mistakes were made, they're not repeated to start with. For most cases, a survey will be required because although sometimes you do have the drawings available on the platform and the conductor, the conditions might have changed quite a lot. For subsea applications, you might have considerable amount of marine growth, or things might have changed and you're not aware. There's also a big aspect to cover during the survey, which is not only the interfaces of the new unit with the existing equipment, but also how are you planning to install the equipment as well. In some of these cases, you're trying to carry out some of the work and you just have the facilities of the platform, so there might be limitations as to what you can or cannot do to sort of solve the problem. So this needs to be considered during the survey. So a good survey really should comment on that installation and should tell you what sort of preparation work needs to take place in advance so the operation can be carried out safely. As well as the conductors, the guides can also get damaged if centralizers have not been fitted in place or if the design fitted is inadequate given the location, specific environmental conditions. Corrosion and lack of equipment can also be a reason for problems with the guides. If you see the pictures on the slide, this shows some typical example of what can happen to the guides if it's exposed to the environment without being protected. A way to prevent this is to, as we sort of were covering a little bit before, is to minimize the clearance available for the conductor to move around. You might think that a good idea is to then just make the guide smaller, but the problem is that you still have to run your drilling equipment. So even if you try to minimize the overall ID, then what you might find yourself is a problem later on when it comes to designing a centralizer, because you will not have allowed sufficient space for a centralizer to be installed or a pre-installed centralizer to be run. So you just have to be a little bit careful with what you design, because you can also be limiting some of your options. This is typically addressed with the installation during the drilling phase of pre-installed centralizers. That will take up some of this gap. Inspection and maintenance plans should also include surveying the guide. For subsea applications as Plazon, this is more difficult to plan because you need a little bit of a challenge in terms of access. So this is why it's important to make sure that during the programmed ROV inspections for the platform, this is included to check the guides and centralizers as part of also of the scope of work. For the cellar deck, platform personnel should be able to check quite often the state of the equipment and if they witness excessive movement. Issues at this level can be quite indicative of problems in the splaston level. So if any problems are detected, it would be a good idea to then check the centralizers at the guides and splaston levels just to see if they're presenting any problems. As I say, it's quite a good indicative to check the condition of the cellar deck, as it might tell you, actually, you should be checking your splash zone, because that's the area where it has the highest environmental loads, as well as highly corrosive environment. So typically, it's one of the levels that suffers the most. As well as the guides, you can also, of course, have problems with your conductors. You can also get damage on the conductors due to excessive impact with the guides and the effect of corrosion over time. If you see the two pictures above, show a couple of examples, quite extreme, on the left-hand side. It's one of the cellar deck level, and the other one shows a picture around the splash zone level. But that's just a typical examples of potential damage or corrosion that you could have on your conductor. As per most issues, regular inspections to record any issues as they arise will help prevent the problem becoming urgent. These regular inspections, together with a maintenance program that addresses relatively small issues as they arise, will save in future big expensive interventions. If damage to the conductor is left unattended, the fix can go from a relatively small repair replacement to a big operation, and that's something that you really want to avoid. Access to the affected areas can also be a complication, and we covered this a little bit before. So you'll have, for subsea inspections and fixes, you'll require divers or ROVs, and then for the splash on level, you typically will require rope access operations just to carry out an inspection of the actual work. And in some cases, it might be considered to install some scaffolding, but the length, the duration, and the scope of work will have to justify that, because this will still involve working at heights and at some point some sort of rope access operation as well. So there's some of the sort of things to consider as well when it comes to carrying out this type of work. As you might imagine, the offshore environment is particularly harsh on equipment in terms of corrosion. This alone merits the regular inspection of equipment to make sure coatings and cathodic protection are working as required. Although in some cases corrosion will be quite visible, in other cases, when the problem is starting from the inside, it can be more difficult to identify. There are two approaches to addressing this type of problem. There is the inside out and the outside in sort of approach. The inside out approach is a lot more difficult as you don't really have visibility of the operation. Apart from this challenge as well, if you're trying to remove damaged casing or conductor, if the internal casings are cemented, then you won't be able to cut and retrieve the internal string, nor confirm if the condition of the pipe left after the cut to run over overshot is good enough for the expected life of the structure of the asset. The outside-in option to address corroded conductors and casing is considerably simpler. Access and visibility alone will greatly simplify the task. Like in summary on that, inside out is less favorable due to inability to inspect casings to verify it fit for long-term service, and inability to properly prepare for remedial work. Problems and then you can potentially have problems if they're cemented. Outside in it will be favored due to the ability to visually inspect all casings, suitability for the long-term use, and the ability to handle cemented casings as well. So overall, potentially the shortest projected time frame as well to complete the whole work scope, and with the highest chance of success and safest option. The pictures shown on the slide show a procedure that we've carried out in terms of basically to drill some holes, to run a probe to measure the wall thickness of the surface casing. There were several wells inspected within the same platform, and the geometry and access for each well were different, which meant having in some cases to adjust the equipment and the procedure as required in order to be able to drill the holes. Another aspect is sometimes, another important aspect in this type of project as well is the tight schedule sometimes at which the equipment will have to be supplied once a considerable problem is found with critical assets. An additional challenge to the schedule is sometimes the limited amount of flights and vessels going to the location as well. So it needs to be coordinated and planned as far in advance as possible. Yeah, on depleting wells, after production rates start decreasing and finally reach a level at which they are not economically viable, the well might require to be abandoned. If the platform is still in good condition and structurally sound, it might be decided to recover the old well and perhaps run a new well making use of the existing guides. This can be done using a whipstock that's shown in the picture in the bottom right. This whipstock is used to drill a new well, but also taking advantage of the existing asset, which is the platform. Another option is as well to install additional slots. But either way, it will be important to have a good understanding of the overall condition of the platform and its remaining life, because that will determine if drilling a new well will pay off, if it's worth considering or not. We already had a look at some of the common problems, and now we're just going to include a few slides showing some of how we have solved some of these problems in the past. We first have a case study for a retrofit centralizer. This is a sort of one of our sort of standard designs of centralizers. New retrofit centralizers in this case were required given the inaccurate position of the regional centralizers and a few others centralizers that have slipped from where they were originally fitted. The picture shows the retrofit centralizer in the open position, which allows it to be wrapped around the conductor, and then that is then slipped down into the guide where the centralization is intended to sit. Something quite important this type of project is the collaboration between the different parties. So you'll have those designing, perhaps suppliers carrying out the installations of C. So it's important to have a good collaboration and discussion amongst all the parties. There has to be that willingness to discuss all aspects of the job and to work together to make sure that you come up with an installation-friendly device and avoid unwanted surprises when everything reaches the offshore stage. Another important thing is also to have a proper factory acceptance test. Make sure that anyone involved with installation as well that needs to be present to come and make comments as well, because there's always final adjustments and changes that can be made to the equipment if necessary, just to help on the final installation phase. This is case study for casing repairs. It's looking specifically into casing repairs around the splash zone level. So the traditional methods of carrying out this work typically involve the use of a cofferdam installation, and that's shown on the picture on the left. So depending on the required scope of work, this might be the best option, because for some type of scope, you do need to have that isolation to be able to carry out the work. However, it is worth, for some cases, exploring alternative options that perhaps do not require that initial task of installing a cofferdam in the first place before the repairs can actually can be completed. An example of an alternative method currently is being designed for a project in the Middle East, and it makes use of a subsea clamp, a load shoulder, a transition sleeve, and a top weldable segments. That's flanges and plates. These are shown in the middle sketch for installation of the 4 components there, for 4 main components. What is not shown there is the weldable segments. And then also that's prior installation, and then to the right, the sketch on the right is after installation, including also the weldable plate all the way to the top. The clamp and sleeve system allows also to have a preservative to be pumped in the void, and that can also be designed to allow for any holes to be wrapped and repaired prior to installation, so the preservative will stay in place. This is another case study for the replacement guide area for a splash zone level. What happened was the splash zone on one of the offshore platform was obviously, because this level is subjected to seawater exposure and high levels of lateral loading from the conductors. In this case, that whole splash zone level was corroded to the point that needed to be replaced in its entirety. So the first thing was to carry out a very good survey, to just basically to determine which structural elements were still sound, were in good condition, that we could use to make sure to support the replacement guide. If you see on the sketches on the slide, the diagram on the left shows in red the original guide, the splash zone and the structural elements as well. In yellow shows the new guide, so you can see how the new guide will interface with the original structure. The picture on the right shows the structure during a factory acceptance test that included a full assembly test as well, which was very important. One of the main challenges for this particular design was that it had to be installed with rope access personnel. So the design was modular, but because of being carried out by rope access personnel, it had to be, each section had to be self-supported in case the rope access operations were interrupted by adverse weather conditions or anything else. So you just have to make sure that once you install a segment, if you had to leave it there for a day, to whatever, it will still be in place when you came back to it to finalize the full installation of the guide area. This was a case for a well support clamp. If you see the first and the third picture, they show a couple of wells that's within the same platform, where the surface casing in this case was receiving no lateral support from the conductor and was taking the whole weight of the wellhead. And this was a big cause of concern, obviously, for the design life of the well. If the samples shown, you can see how different one case is from the other one. As I say, both of them within the same platform. So they're quite different in terms of the height from the base of the wellhead and the top of the conductor. And if you see a little bit in detail, you'll also see that eccentricity is quite different as well. In order to design a suitable well support clamp, a detailed and precise survey had to take place in advance, and just to make sure all the correct measurement was taken, and just to avoid any issues during the installation. So you wanted to design a clamp and go install it and make sure they would fit properly at location. Once the clamps were fitted, and you can see them fitted in pictures 2 and 4, the wellhead load would then be transferred to the conductors, which is why it was important also to verify the integrity of the guide as well as the conductor. The repair options are based on previous experience or industry knowledge, but the effectiveness of each option is governed by factors such as I mentioned before, the integrity of the conductor and the integrity of the guide as well. So it's important those 2 aspects are also checked. This was a case study we did for an additional guide. This was an additional guide for an H platform. We carried out a complete analysis of the structure and the clamp-based additional conductor guide design to make sure they could support the well without negatively impacting on the platform. As well as that, we prepared project-specific installation procedures, also for the installation via rope access. The guide was lifted over the side of the platform, then slung into place within the jacket structure and firmly secured within a few hours by a crew of 4 abseilers. So what we did was install a temporary guide in the opening through the cellar leg to provide some sort of guide to it, and then we could run on the drill string to sit on the guide. Once landed in the guide, the bush, which had a polymer lining and formed a clearance feeder on the drill string, was locked in place to provide the necessary restraint at the critical point. With the initial drilling complete, the temporary guide was removed and the conductor was run into the hole. And it was all completed quite successfully. This was a case study for a client that wanted to recover a slot on a platform in the North Sea. But the 20-inch tieback riser also needed to be retrieved. However, there were some concerns on the integrity of the connectors, because previously same type of connectors have failed during a slot recovery operation, which basically resulted in a drop riser, which is quite dangerous. So what we did was supply and run a 1338 casing string complete with a smart anchor packer inside a 20-inch tieback to internal that dual string recovery. So that internal casing riser provided a structural strength and integrity to the 20-inch riser, so to be able to retrieve safely. As well as this, we also supplied expandable grip pin mandrels, little pins to secure the strings, and also bandsaws used to cut piping sections for disposal as well. As you can see, we have seen quite a few examples there. In terms of a conclusion, I would just like to stress the importance of considering the structural integrity of an asset during its design life from the very beginning of the design phase. And this should consider allowing also for inspection and maintenance, which are key. The design of an element has to consider its environment and all the interfaces and potential access problems it might face during its design life. As we said, some of the offshore assets might be designed for 15, 20 years, but this doesn't mean that they don't require inspection and maintenance work. That still needs to happen. Asset integrity repair projects or asset life extension projects is always quite bespoke in nature. And in order to design and supply a suitable solution, keeping good records of the equipment and any changes that might have taken place is very, very important. If these records are not available, expensive and extensive service might be required, and there is a potential of a chance of success of the project to diminish if that happens. And as again, just to stress again, the implications for the commissioning, poorly kept assets are a lot more expensive to the commission and present a higher level of risk as well to carry out this work. So I think that's all from me.
Okay, thank you, Anne. I hope you all found today's presentation interesting and helpful. As mentioned before, unfortunately the Submit Questions chat pane located in the control panel is not available today. However, if you have any questions or feedback about today's topic or other areas of interest, please submit your questions to info@claxtonengineering.com, which is on your screen now. If you would also like to receive the latest information and news from Claxton or subscribe to the Claxton Thought Leadership blog, please visit claxtonengineering.com. And of course, please follow us on our social media channels, including LinkedIn, Twitter, and Facebook. To close the webinar today, please exit by clicking on File Exit. And thank you again for attending today's session, and we look forward to seeing you at our next webinar.